Let's start with the last few things about MOSFET. One of the things which we are yet not done and which is more relevant for the future courses is equivalent circuit. And we want to know what is the equivalent circuit of a MOSFET. Typically, as I said other day, if you have this N-channel device, you have 4 terminals, gate, source, drain, and we want to know its equivalent circuit. Basically it should look something like this. We don't know whether it is right, but that's what we are looking into. Okay. Right now, for the simplicity, some other things are neglected by me, and I'll show how the actual circuit will look. We can put either capacitor or this is the equivalent circuit of a MOSFET, okay, which we'll use in our circuit analysis later. This is a figure which is shown here for an amplifier which has a load impedance of Z out. It can be either R parallel C or only C. That's not part of our equivalent. This is something external. Input, of course, is always external. So this is the equivalent circuit which we are looking into. Okay. So this is called small signal equivalent circuit. Of course, there is nothing N or this is all both devices are same equivalent circuits. Firstly, we would like to see whether this so-called equivalent word, how much is equivalent from the device itself. Let's say it's an N-channel device. These are your source drains. This is your gate oxide. This is your gate contact. Source drain. This is your bulk. So these are the 4 terminals which are represented here. Okay. And we want to know if in a circuit this is what I do, should I or am I right to represent that in this form? And if I do so, then I can solve my circuits, because this is my device. This can be some inputs, this can be external outputs, loads which output I can take. This is an amplifier which is shown here. So let's quickly see what are the things we are worried about. Let us say IDS is the net current which is equal to IDS plus IDS. The net current, drain to source current, is combination of DC current plus an AC current. Okay. We also have relationship. We know IDS, we have written earlier. Let's say it is N channel, so mu n Cox, W by L. Let us say it is in saturation for the sake of something to be done. If this is so, then I would say VGS is also equal to VGS plus VGS. The gate to source voltage total is sum of DC gate to source voltage plus AC signal superimposed over it. Okay. This is called small signal. What does that mean? That the AC signal magnitude or amplitudes are much smaller then the DC value is much smaller. Typically the input signals may vary from few millivolts to tens or 20 millivolts, whereas DC values may range from 1.2 volt to 5 volts. So these values have to be understood that these are called small signal because the DC value is much, at least orders higher than that of the AC signal. So if I substitute this like this here, IDS, then I say I substitute here half mu n Cox, these are all constant. So I keep here, and for VGS I substitute VGS minus VT square. If I expand this, I can get half mu n Cox W by L VGS minus VT plus VGS square. Is that okay? Now if I collect the terms and represent this finally, just look at the way this has been done. I take VGS minus VT out from here, so I get half mu n Cox W by L VGS minus VT square. I take it out. So what should be in the bracket? 1 plus VGS upon VGS minus VT square. This factor, I take it out of the bracket. Okay. So I get 1 plus small VGS upon VGS minus VT, square terms remain as there. What is this value? IDC. So what I'm going to get, maybe I can rub up this, we don't need circuit figures right now. So I say capital IDC, IDS is IDC 1 plus VGS upon VGS minus VT square. Is that clear? Once I get this, if I say VGS is much smaller than VGS minus VT, binomially I can expand that, and this can be written as first term higher, only I use 1 plus 2 VGS upon VGS minus VT, small signal. Then I can do all this, and what I am going to get is IDS. Okay, this many times in the book, which I should also tell you, this kind of current, when I write square, is actually written a word ID sat. Why it is called ID sat? Because it is the saturation current of the transistor, so it is specified as ID sat. And this value is actually specified by the manufacturers. What is the ID sat versus VGS value you have? Okay, this is a spec which will be given to you. So that's most important. This is the ID saturation, and this comes from the fact that for a VGS, whatever is this value, let us say it is IDS versus VDS, at 1 VGS, this value is essentially the saturation current of the device. Okay, and that's why we are interested in this, because in few things you should remember. In the case of analog circuits, transistors will be always in saturation. Is that word clear? Please note down, this is very important for us, and that's why we are doing all this. For analog circuits, that is for amplifiers or any other circuit related to analog, device is always kept in saturation. And in digital, that's very interesting. In digital, what is digital inputs will be a pulse. So if you see this digital inputs, PN like this, VGS, 0 to VDD it will go. That is the power supply value. Swing from lower to higher value. And at different values of inputs, let's say DC, we don't say actually it moves like, but for these two values, if you see equivalently stepping up, the transistor will change its state. Transistor will change its state. If VGS is 0, transistor is off. If VGS is VDD, so what is this VGS? VDD minus 0, which in this case it will go to 0. Okay, this is my inverter, RD. So we see when this is maximum, this transistor is in non-saturation full because VGS is much larger now. So VGS minus VT corresponding to this VDS, because current will flow, drop will come, this will be smaller than this. So device will be in non-saturation when VGS minus VT is much larger than VDS. In between, when you cross your VGS beyond VT, VGS minus VT is very small quantity. You are just crossed VT by some amount, so VGS minus VT is very small. But corresponding with, since the device was fully off that time, what was the voltage here when this device was off? No current, full VDD. Since this was VDD and you have just crossed VT, that may fall down, but still VDS will be larger than VGS minus VT. So the trick in digital circuit is, device wakes up in saturation. Wakes up means when it turns on, it actually enters saturation. It looks a little odd from our characteristics, because if we are saying that, oh, it should go from linear and then go to saturation, the device actually wakes up in saturation, and as input rises, it enters non-saturation. Is that clear to you? So this is in digital, the state of device varies as the input starts rising from low to high or changes otherwise from high to low. Is that correct? So in the case of digital, you have to figure out every time what is the status of a transistor and then correspondingly use the IDS equation whether it should be non-saturation current or the saturation current. Is that clear? Whereas in analog, device will always remain in saturation for BJT also. But there the word is not used, saturation. There the saturation has some other meaning. In fact, now you have said it, here it is called linear region, in BJT it is called saturation region. Okay. So don't get confused now. So right now keep BJT away. So in a MOSFET, when the actually current saturates, we say it's a saturated region. Okay. In that case, VGS minus VT always will be smaller than VDS. Device will remain in saturation. And the current which it can flow at the maximum is given by that equation. So in all analog circuit, why we looked into analog? Because this is an equivalent circuit which I'll use for amplifiers, analog circuits. This will be a sinusoid inputs and we'll like to see sinusoid outputs. Is that correct? This is my signal and that will be my sinusoid output I am going to look into. Therefore, device should be maintained in saturation mode. How can I maintain a device in saturation in analog? I'll show you later. One is of course bias it something like this so that this voltage is always sufficient enough to keep it into saturation. So that VGS is always smaller compared to the net voltages. You can say biasing the circuit. The alternate method which all integrated circuit people will use is bias through the currents. This word you should now remember. This is RDC. So it is bias DC and therefore this current value is so chosen that the device for given W bias remains in saturation for all input signals. Is that correct? So this is how all integrated circuits will be biased. Nowhere two resistors will be put there to bias the circuit, whereas in the lab probably you will be putting resistors and trying to bias by voltages. Here it can be biased by, you can think why I can bias. If you see this equation, when I fix this, I am fixing this. Is that clear to you? If I am fixing this, I am fixing this. Is that clear? So if I have a current source, I am actually fixing VGS there, which means I can bias the device by even current sources. The current can be either in the what we call near power supply, or it can also be somewhere here. What is the difference between these two currents? This is called current source. This is called current sinks. Okay. So either you can have a current sinks biasing or you can have current source biasing. You can do either of them. Okay. Please remember, this is how all circuits are biased inside an integrated circuits. Nowhere I put resistor. Why do I not put resistors? Any idea? Okay, I have not done technologies very much. You will not immediately appreciate. Resistor is made out of some diffusion area, either P area or N area. Okay, and the resistance is proportional to what? Rho L by A. Is that clear? So rho, which is decided by the doping there, Q mu N, 1 upon Q mu N or Q mu P. So the doping decides the resistance and size decides the total resistance. Okay. So that means if you want 1K to 100K or 1 mega ohm, the size of this resistor will be so high, large, for a given possible P and N we can dope in a technology. Let's say it takes 2 mm by 2 mm to create a 10K resistor. The chip itself is less than 2 mm by 2 mm for the transistors you put. You may put hundreds and thousands of transistors in that area, but you may actually require only one resistor there. So you cannot use resistors normally in any of the integrated circuits because they take hell of an area. So how do I create resistances then? From the transistor themselves. Transistors have linear, saturation, larger resistance, smaller resistance, W by L you change, size is still smaller, and you can create resistances in using the transistors themselves, and they are never used externally as resistance. But some circuits in analog do require resistance. It's not true that they are never used, but next semester course, whosoever teaches you analog, he will explain you why resistances are essential there. Okay. Okay, so this is all around things I said. So now let's see, once I decide that I must find out equivalent circuit of this. Okay, this is the equation, and if you look at very carefully, if I remove IDS, then IDS saturation, IDS means AC current, can be written as this mu C of X, everything will be talked as beta. So the value I am going to get, beta VGS minus VT square, beta VGS minus VT into VGS. So ID sat by VGS is what value? ID sat by VGS is what is the name I should give that? Current by voltage. Transconductance, IDS is the output current, VGS is the input signal, this is GM. Is that clear? And GM is beta VGS minus VT. Of course, if you get into the current way, you can prove this, it is 2 beta IDS. So why this equation is necessary and not this? What is the difference between two? They are same. But why I showed you both? What does this mean? DC biasing using resistors. This is voltage biasing. This is current biasing. So if I am doing current biasing, I can directly find how much is my GM. If I am doing DC voltage biasing, I can still find my GM. So these two equations, as I say, I am preempting you for the next course, but just to tell you from where these appear. Okay. So if you see this AC analysis, similarly you can do for, yes, Pawar. Okay, this all currents are sat. Okay. All are, as I said, device is in saturation, all are in sats now. Okay, that initially I did not say, and that's okay. As I say in analog, all devices will remain always in saturation. Okay, so I can similarly find the method which I did. G0. How much will be G0? Conductance. Conductance should be something related to IDS. How it will be? Or rather I should put R0 for you. It can be shown. R0, we have already derived this earlier. So R0 is this. So now I got this value. I got this value. Is that correct? I got the GM. I got the R0. So once I bias a device, I know my R0, I know my GM, and let us see if that is so. I am using certain frequencies in which all capacitance can be neglected. What does that mean? Raj, if I say I am having frequencies in which all capacitance effects are neglected, what should be the frequency order? When the impedances will become dominant at high frequencies, So right now assume low frequency small signal analysis, and in that case the equivalent circuit will something look like this. This is VGS, this is source grounded, GM VGS, R0, okay, call it drain or output. So what is V0 now? Give me expression for V0. अरे इतना आसान नहीं है, थोड़ा सोचो ना. Minus, that is what it is, GM VGS R0. Okay. So V0 by VGS, which is nothing but input. VGS is input. Vin is same as VGS. Okay. So V0 by Vin is equal to call gain, and since it is frequency independent, it's called DC gain. Why it is called DC? DC means zero frequency. But this is not really a DC gain, in the sense the signals is small signal, so it is not a DC gain, but all analog people, which is frequency independent values, they declare that as DC gain. So A0 is equal to minus GM times R0, which is called DC gain. In case there is a load resistance here, RL, what will change here? Net gain then minus GM times RL. Or if any other capacitor, it will be parallel to that itself. Is that okay? Is that word clear? So an amplifier which has a load, what is the actual amplifier shown there is this. I am having a resistance RL, okay. I am biasing it some other way such that I applied a V in here, I take a V out here, and this will be my gain. Please remember, these two values are decided by which quantities? You look at those expressions. Which quantities decide those? The DC biasing values, AC equivalent circuit, the values are decided by DC biasing values, and that's most important. Therefore, in a circuit, where do you bias your device will decide how much best GM and R0 you can get. R0 from the characteristics, what will be R0 here? The slope of this characteristics is nothing but I by RV is G. So this is the R0 value. Is that correct? Now the trick is something you can see from the two expressions which I wrote. Sorry, I should keep writing. We figured out if I increase IDS, I increase GM. Is that correct? But if I increase IDS, I decrease R0. Is that correct? That means larger currents may lead to larger, but it goes even root and not even directly proportional. So GM rises root of IDS, R0 go inversely as IDS. So in fact, increase of IDS does not increase GMR0. Is that correct? GMR0 is also called intrinsic gain of a transistor. Why intrinsic? No loads, no external circuit. Intrinsic gain of a transistor is GMR0, and if you increase GM, R0 goes down. If you increase R0, EM goes down. So the product does not change drastically as everyone thinks. Oh, I can make huge gains. Okay, it's not easy. The alternate method there should be, if I cannot change IDS, how can I increase GM? So it's beta. Beta is what? Mu Cox W by L. So if I use N channel, mu L will be higher than mu P. So first I should use N channel device and then increase W by L's to increase this GM. And then R0 will be decided by whatever IDS I fix. So I can only increase the GMR0 value if I increase the size of a transistor. W by L is size, W and L. If I increase the size of a transistor, then I say I can increase gain of any amplifier. Is that correct? So you will see that larger the W by L transistor you put, larger gains you can attain. If I increase IDS, what effect in circuit I'll have other than this GMR0 thing? IDS into something, VDD, power supply into IDS is the power dissipation. So larger the IDS are used, larger will be the power dissipation. Is that clear? That is something which may worry us because the power will be given to us. This is the maximum chip should actually dissipate. Okay. There is a word which I use often in the project in masters when you come out your degree, that I want to design a low power amplifier. Now this is a very interesting word. Power, क्या meaning समझते हो? Low power amplifier. The power amplifier is delivering the power at the output. Larger the delivered power, better is your power amplifier. But this earlier word low power means power consumed in the device should be low, higher delivered, lower consumed is called low power amplifiers. Okay, so game in all the circuits is to make low power circuit. Power means delivered should be larger, consumed should be smaller. This is what designers do. This is where they keep playing with the parameters to suit for given specifications. Is that clear to you? So this is some way design connections which I thought you should know in second year, because many of you will never do anything later, so at least yahan seekh lo. Okay, now let us see if I wish to know what are these capacitances. Okay, I can then start doing little bit of theory back. I want to know what is this capacitance. Let's look at the transistor once again. Okay, there are three states. थोड़ा बाद में सुन लेना यार. Okay, this as I said is channel length. Okay, let us say source is grounded and bulk is also grounded. However, you will apply VDS and you will apply VGS. For N-channel device, let us say this is what we will do. If VGS minus VT is greater than VDS, what is the state of a transistor? If VGS minus VT are essentially saying VGS minus VDS is greater than VT, so what does that mean? Channel exists throughout, so you are in non-saturation. Okay. Since you are in non-saturation, now you can see Gate sees how many capacitors? Gate sees there is a capacitance of oxide with the channel. But there is no, of course there is a depletion capacitance here, but there is no connection now between this and the bulb. So a capacitance which otherwise would have come is called CGB. Let's say device is in cutoff mode. No channel. VGS is less than VT. Now what is the capacitance is seeing from gate to the bulk? Because there is no channel, so CGB is the capacitance which gate will see to the ground. Is that correct? But if channel exists, if the channel exists, it is CG now with channel. But the way we do is, this is some kind of an interesting theory. We say, okay, though it is a distributed capacitance, but because everywhere channel has different potential, so it has a different capacitance everywhere, okay. So we say, okay, if that is so, do some lump model. We say half the capacitance is put to gate and half to, call it dash if you wish, because I am putting area on the drain side. It's called lump model. What is lump? Total capacitance distributed as if averaged out, half is ascribed at the source end and half is ascribed at the drain end. Is that correct? This is our method of putting lump models. Then at that time, how much will be CGB? 0. Why? Because we are talking right now of non-saturation case. Channel is existing everywhere. So the net capacitance gate, which I may say CG dash something like this, is actually Cox WL. Sum of these two. Total capacitance seen from gate is Cox into W by L, W into L. Cox is capacitance per unit area of the oxide. What is Cox value? Epsilon ox divided by Tox, which is specified for technology. Tox is a technology parameter, thickness is fixed. Silicon dioxide, if used, epsilon is fixed for that. So this is fixed. But the value will change with size, W by L or W into L, area. Now there is, apart from this, I see another capacitance sitting here. Because of the technology I do, this oxide also has some overlap over drain and gate and source. This is called overlap capacitance. Is that point clear? The capacitance so far we have seen was this, but there is a capacitance associated here. Okay. This is called overlap capacitance. So you can see C overlap for source side is how much? Let us say some value. W into L of course is area. If L is LD is called the overlap. And in general, source and drain will have same overlaps. In general, but in asymmetric device, this may be different. So W into L into Cox. Only thing area for the overlap is W into LD. In the channel it was W into L. In the case this, it will be W into LD, which is true for both source as well as drain, because we assume LD is same both sides. If they are not there, you have to put LD at source side separate from LD at drain side. These capacitance essentially also add to the, from the source side if I look at it, I should also write W into LD into Cox is the net CGS you can say, or CG in you can say, which gate will see, or plus this also. Both of them will get added. Okay. So this is the net capacitance which gate sees in real life. Is that clear to you? In case of saturation, what will not be there in case of saturation? Drain side, there is which capacitance is only available on the drain side? Overlap. But the net capacitance now is ascribed fully to the source side, and one says in case of saturation, okay, since I have duster, you rewrite. Once the channel is, N channel is created, the bulk is screened. Okay, because the capacitance is only depletion there, which is much larger. So, as if we are saying, this capacitance, this gate has no more control on this area, it's a neutral area now. Okay. Whereas there is some, I have not yet finished all of my capacitance. There is some more capacitance as I am now seeing. This is one I see. So what is the total capacitance here will come? 2/3. CGD dash नहीं है उसमें. However, it is always said, even if this is 2/3, if I assume it to be 1, so for universally, what can I take? Cox into W by L is the capacitance available to me at the input. In saturation, I am overstating that value. In saturation, it was okay anyway. So in most cases, we do not use 2/3 values, we use only Cox into W by L as the value at the input plus overlap, of course, plus overlap capacitor. In the case of saturation, how much is CGD in fact? Is CGD dash, plus overlap capacitance WLD into Cox. So if I now see my transistor, once again carefully, okay, but some more capacitor. There is a depletion layer associated here. What is this? This is a PN junction. Under zero bias, it is also reverse bias. But this side is really heavily reverse bias. So I have two more capacitance. This is called CDB and this is called CSB. Sorry, I should put capacitance. And how will you calculate these values, CSB and CDB? Assume step junction for this value of voltage for the given doping of substrate. N plus P is a step junction, so N plus you forget about it. So only P side depletion. So evaluate W is equal to under root twice Ks epsilon by QNA into voltage. In the case of source, it is only 2 phi F. In the case of this plus VDS value you have to add, figure it out, then find CSB and CDB. So if I use all these capacitances in my circuit, I say, okay, here is the circuit. This CGS actually contains which capacitances? The CGS dash coming from the source side capacitance, whatever you are getting, plus between source and the bulk, there is a capacitance. If this is your bulk, this is CSB. Is that correct? Between drain, let's put Z out. Between drain and bulk, there is a capacitance which is CDB. Is that clear? So in real life, this will be the equivalent circuit of a MOS transistor. For simplicity, we say that source and bulk are at the same potential. So we neglect CSB in many cases. We only use CGS and you put a equivalent capacitor CDB here and remove this part from here. Is that clear? If the bulk and the source have the same potential, we say okay, it is CDB, same as CDS, and therefore you put the capacitance here. What is this value? CGD is because of what? Mostly overlap capacitance. In saturation this will go. In saturation this will go. In non-saturation both will appear. In saturation this will go. Only this overlap capacitance will come. So analog circuit is only overlap capacitance. In saturation it's only the overlap capacitance. Okay. This is very small. What does that mean? Very small means, if this value is very small by number, where it will start operating for you? Let's look at a circuit. You have a capacitor between input and output. This is your CGD. When it will influence directly for you? When 1 upon j omega CGD should be higher or lower? If it is higher, it is good because it will open. Okay, higher means what? W should be smaller. So at low frequencies, CGD, 1 upon j omega CGD is very, very small, very, very high. So it is like an open circuit. Is that correct? But at higher frequencies, this may give you some equivalent Z. And therefore input is now connected to the output through this. Where do I show in my transistor there, which this device will show you? Now you see the capacitance. This is which value? What is this value? CGD. This is CGS. There is a CSB. There is a CDB. If this is my out drain side, this is my input, which is my gate side. What is this capacitor is doing? What is it called in circuit? Output is connected to input through some impedance called feedback. So CGD acts like a feedback capacitor. Is that at what frequencies? Much higher frequencies. So the limitation of an amplifier actually comes from this feedback capacitance, which is CGD. Is that correct? Which is very small in general, but at higher frequency, this may have influence of returning some output signal to the input signal. Is that correct? This is very, very important in all analysis of analog blocks ahead, because this CGD limits you. Is that correct? CGD limits you. So now we see this is equivalent circuit of a transistor under all frequencies. Okay. If I say low frequency circuit, then what should I remove? All capacitances can be removed from here, and once I remove all these capacitances, the circuit just is simple. Gate to source open circuit, VGS, correspondingly current source at the output is GMVGS, across it is the resistance, which is the output resistance of the transistor R0, and therefore you can always evaluate the gains. Is that correct? Always evaluate the gains using MOS amplifier. This is how we actually perform all analog designs using this. Okay. Next semester, more details. Okay, so we are now seeing equivalent circuit. We are also seeing this. The last but not the least of importance of this, which I thought maybe, as I keep saying, you will never learn things ahead in this kind of area. So I just noted down few things for you. Okay. Please read the other book, which is this Niemann's book, for further details. Okay. As I said, in a MOS transistor, this channel length and width which we are using, initially we started with 100 microns. In 70 or 65, first transistor was made which has channel length of 100 microns. By 78, L became 5 micron. This is around 65, this is around 78. By 85, we were working on 1 micron or even 0.8 micron. By 95, we were working on 0.25 micron. By 2000, we started working on 0.13 micron, which is called 130 nanometers. Okay. And afterwards, we run through now, we went to 90 nanometers, then we went to 65 nanometers, then we went to 45 nanometers, then we went to what are these numbers? These are not channel lengths. What did I say earlier? If you see, I want to double the density of the chips and transistor on the same area. What is the way I said? Double means 0.7 into 0.7. If I scale this technology by 0.7, area will scale by half. That is the double the density. This is what we thought. You can see each number is 0.7 of this. In initial times, whatever technology number was, same as was channel length. For example, now 65 nanometer uses 45 nanometer channel length, 45 is using 28, 32 is using 22 nanometers, and further down it will come. The current technology which is marketed is 28 nanometer, which is actually 32 nanometer process, which has these numbers they are giving. All Intel chips or IBM chips or TI chips are on this technology, which has the oxide, this channel length of the order of nanometers, which is 16 to 20 nanometers depending on each process you are using. This is called scaling. Word used is scaling. What was the scaling word means? You divide the earlier dimension by some number and you get the next technology. Assumption was what? That if I scale every quantity I use, then the performance should not change. If I scale everything, then performance should not change. And we first tried that. So we have two methods of scaling. One is called constant field scaling. This is very important, which we don't use at all now. Earlier we used it. Constant field scaling. What does that mean? Field means what? Voltage by length. So if I reduce length by same amount, I should reduce voltage. So the field remains constant. So I have the two scaling methods. Let's say L was the old L, W, I'll give you the area, Tox, parameters, Xj. What is Xj? Raj? Whatever is source drain depth is called the junction depth. Okay. Xj, VDD, power supply value, threshold, dopings. Doping could be either any of the substrate or ND. If I scale, the new process is L dash is L by S, W dash is W by S, where S is called scaling factor, which is larger than 1. Okay, which is larger than 1. S is a scaling factor which reduces the dimensions by some number. Area will go how much? Square. Okay. Tox is Tox by L, S. Okay. Xj dash is Xj by S. VDD dash is VDD by S. VT dash is VT by S. Everything. Only thing is, NA dash will be S times NA, unless you increase VT cannot be reduced, okay, correspondingly for devices. ND dash is S times ND. Okay. Now, if I look at the values, Tox dash will be how much? Epsilon ox by Tox dash, which is epsilon ox Tox into S. So it is S times Tox. Okay? The new scale capacitance is epsilon ox by Tox dash, the new thickness, but new thickness is Tox by S. Yes, 1 minute. So this is S into Tox. I'll quickly write down few of them. W by L will not change. Is that correct? Why? W and L both scale, so they don't change. Then most important is mu n Tox dash is mu n Cox into S, and therefore VGS dash minus VT dash is 1 upon S VGS minus VT. Then VDS dash is VDS by S, and therefore if I calculate ID SAT, new one, how much it will come? Anyone? From the old one? It will reduce by IDS by S. Substitute all these values are given. So the new ID SAT will actually reduce by the old value by S factor. Is that correct? So what will be the power reduction if VDD also scales and power also scale? The new power dissipation is old power dissipation by S square. So what is the advantage I got? Low power. I reduced the power by scaling. I scaled the device, the power dissipation went down by S square. Is that correct? That's something I was looking for. But this is under an assumption that everything is scaling. In reality, voltage does not scale in the same way, because I cannot reduce 5 volt to 0.05 volt because you scale by 1000. Okay. I cannot have battery of even that value which is accurate enough. So I cannot scale the voltages very much. And if I keep my voltage constant, then I say constant voltage scaling, the first thing will change is what? Fields, because voltage is higher, other things reduce. And as field rises, the device physics change, because the fields are high now. Okay. We'll see next time what are called short channel effects. If I reduce, what things can go wrong. Okay. See you then tomorrow.